Good morning. Welcome to our first official live class for Chem 100. Sorry, we were supposed to do this last night, but I was having some internet issues, so we're doing it today. Hopefully you're able to join in. I'm not sure if anybody's out there. If you are watching, if you could just leave a message in the chat saying hi so that I know that you're there. It's also good practice because that's a great way to ask questions as I'm going through. So if I know that people are here, we can make it more of an interactive class. I can pause and ask questions and ask you to do some stuff that will help you to learn the material. So we'll usually start more or less on time, but we'll kind of just wait a couple minutes here for people to join in if they want to. And you can see behind me here is our H1 first handout worksheet. We're going to talk through this together, and I'll explain some of the things and kind of point out what's important. I'm also going to leave a lot of it blank. That's just because I want you to be able to try this stuff on your own. When you turn this in on Blackboard, I'm not going to go through and grade it item by item. This is just meant to be some practice, some notes for you to work on it. So all I want to see is that you kind of went through some or most of it, and then you can submit it. If you're having trouble with YouTube, as you can hear in the background, I also have the Discord app open, so you can send me messages there. It should be more or less synchronous to what we're doing. Sometimes there's a little bit of a lag with YouTube, but usually it works out okay. So if you have a question or you want me to go back over something that I already talked about, please let me know, and we'll do it. All right. Let's get started. So today we are going to talk about the scientific method and defining some terms in the context of the scientific method that are a little bit different from how you might have understood these terms before. Then we're going to look at measurement and uncertainty, and that'll be it for the first unit. So first, how do you use the scientific method? Now, you've probably heard of the scientific method before. You've probably gone through the different steps of it in previous classes. So just kind of as a reminder, the idea is that you're seeing some sort of observable phenomenon, and then you're making a hypothesis about what's maybe going on. How do you explain this observation, this phenomenon? And then you're testing that hypothesis to see if it works or not. And if it does, you continue to gather evidence. And if it doesn't, then you refine your hypothesis or change it, test it again, and so forth. So that's the basic idea. So here's an example. You push a power button on your remote, and the TV does nothing. Now, there's lots of different reasons that could happen, right? So, for example, there could be an invisible fairy here that absorbed the energy from the remote. So you hit the remote, but there's an invisible fairy in front of the remote who absorbs the energy, and it didn't get to the TV. All right. So that is not a valid hypothesis. Why is that not a valid hypothesis? It can't be tested. It could be, it can't be disproven, let's say, but that's not the point. The idea of a good hypothesis is something that is testable. We can't know if the fairy is there absorbing the energy. So that's not a good hypothesis. Whether or not we think it might be true, it's not a good hypothesis. So we'll try something else. What if the TV didn't turn on because the remote's batteries are dead? That's testable, right? We could change the batteries, and then does it work? Well, then that's probably what happened. If we change the batteries and it still didn't work, then we have to adjust our hypothesis. So maybe there's something wrong with the TV. Maybe the remote itself is blocked, or there's something wrong with the buttons. There's lots of other different things that we could then go step by step and test as we refine that. All right. So ultimately, when you make lots and lots of observations and hypotheses about a given phenomenon, then these can kind of be collected or codified into things that we call laws or theories. And these are two words that are very, very misunderstood in the scientific context. And I think it's because we also use these words in non-scientific contexts. Like law means something in our everyday life, even though it's totally different from a scientific law. Theory means something in our everyday life, even though it's totally different from a scientific theory. So let's talk about the definitions of a scientific law and a scientific theory. All right, so a scientific law is a brief statement that summarizes multiple observations and predicts future ones. So it says, when this happens, or changing this makes this change in this way. And that's something that seems to happen every single time. So note that a law is not like the common idea of a law is it's this like absolutely you can't criticize it, you can't deny it. It's like it's absolutely true. It's a law. That's not correct. That's not the definition. A law is a set of observations based on evidence that when this thing happens, this thing generally happens. So it's considered a lower level of scientific knowledge because it doesn't explain anything. It doesn't say why this is happening. It's just, oh, every time we do this, this seems to happen. So the law of gravity, things like that, where you can say, oh yeah, well, like every time two masses are near each other, we can predict the force between them using this equation. It doesn't say why or what's causing that, just says that's happening. So that's a scientific law. All right, good question. Can you consider a law like a cause and effect? Yeah, that's sort of how, well, okay, let me say that. In many cases, it comes out that way. But there's also other ones. Like, so, for example, if you think about, like, again, gravity, the force between two objects is explained by an equation. And so it's not exactly a cause and effect because there's nothing causing that gravitational pull except for the mass. It's just that it's happening and it's described in a particular way by a particular equation. Same thing for something like laws of motion. Like want to calculate a trajectory of something that you're like shooting off into the air. You know that it's going to follow certain rules, and you can do that. So sometimes it's cause and effect. Sometimes it's just saying that things are associated with each other. But the main thing is it's just the observation. It's just this is what we're seeing, and it's not why is this happening? What is causing this to happen? It's just this thing is happening, and it seems to happen all the time. So, for example, every time it's raining, people are late to class at Harper. If we see that over and over again all the time, and it seems to keep holding, that is kind of a cause and effect one, like you say, that we can say that that's like the law of student weather. It doesn't say why, it's just a thing that's happening. So then the higher level is what we call a theory, and the theory explains what's going on to make that effect. So for the law here back to the TV example, the TV will not turn on if it's unplugged or if the power is out. The TV will not turn on via the remote if the remote's batteries are dead. That's just sort of, what we see. But then the theory could be why is that happening? Well, there's no power source. There's not enough power in the remote to make the infrared beam that goes to the TV and turns it on, like that. And so both of those need to be verifiable. They need to be testable with experiment, and they can be refined or supported or unsupported depending. So the common idea is that theory is just like some idea that you have that may or may not be true, and then once you test it enough, it becomes a law. And that's totally wrong in the scientific context. That's not how it works at all. A law is the set of observations that seems to always happen, and the theory is the explanation behind it. And there are both laws and theories that are extremely well supported by evidence, and there are ones that have been changed over time. So for example, atomic theory, the theory that all matter is made up of atoms. Not controversial, right? There's a lot of evidence, I would say an extremely high certainty that is in fact true. But But it's a theory because the atomic theory, saying that things are made of atoms, explains all this other behavior that we see, chemistry and physics and stuff, because we can explain that in terms of what the atoms are doing. So please get rid of your old ideas. It's really hard to do when they're stuck in your brain, but get rid of your old ideas of laws and theories and try to focus on these new definitions if they're new to you. All right, so let's do some examples here where we're looking at some part of the scientific method and then trying to figure out what that's referring to. All right, so a person had a pound of fish, a pound of salted fish. 1 week later, the person saw the salted fish was still good, but the unsalted fish had spoiled. So I'd just call that an observation, right? You had this thing and you observed it. So that's an observation. Okay, so part B. The person thought the salt kept the fish from going bad because the salt lowered the bacterial growth. So what would we call that? That's probably more of a theory, right? That's attempting to explain what's causing one versus the other. It could also be we could also say this is a hypothesis, I guess, because it's just a first idea. So this would really be, because it says the person thought, it's not really verified, it's not tested, so not a theory. I would call this more of a hypothesis. So we called this an observation. The first idea was the hypothesis. So now they got another pound of fish, different kinds of fish, different salt levels, measured each one for a month. So that is experiment. And then D, this is kind of confirming the hypothesis, but after a lot of evidence, after a lot of experimentation, we can probably call that a theory that we're developing now. Right? Once we have that evidence, once we've done the experiments, now we have a theory as to what's happening. One thing that you don't see here is law. So where would law fit in here? Law would be like saying that unsalted fish spoils, salted fish stays fresh. Right? That's the law. If that happened every single time, we could say the law of fish is if it's unsalted, it spoils, and if it's salted, it stays fresh. Doesn't say why, doesn't explain anything, but it happens over and over again, so that could become a law eventually. All right, so we'll give you some chances to work on this as well. As I said before, I'm not going to grade these and go point by point through them, but if you have questions about them or you're not sure of the answers, please ask. You can ask on Discord, you can ask in lab in person, you can send me an email, whatever. You can ask right now if you're looking at it on YouTube. But if you don't understand something here, you're not sure what the right thing is, please ask. Let's look just at this last one. Which of the following is a testable hypothesis? All right, so A is not testable because we're dealing with something that is subjective, more beautiful. B is not testable, or I'm sorry, B is testable, right? Because we can test a bunch of plants and how much sunlight and see if they need 5 hours or not. So C is not, again, subjective, and D is speculative in the future. We don't have a good way of testing that unless we have access to the future. So B is the testable hypothesis here. All right. Any questions about laws, theories, scientific method before we move on to measurement? All right, let's go on. Sorry, this table doesn't quite fit as nicely. So here's just a general table of measurements. You've probably heard of a lot of these things before. We have what we call the English system or the imperial system of measurements, sometimes of the US system of measurements. We have the metric system, which the rest of the world uses. And In lab, in science, we're generally always going to use the metric system. But in our everyday lives, we also encounter the English system units. So it's good to be able to know a little bit about how to go back and forth. We're not going to deal with unit conversions in this section. We'll get to that a little bit later in the semester. But we do want to know what types of units we're going to use to measure things. So mass in the English system we think is pounds, but it's actually this weird unit called a slug. Pounds is really a unit of force. So pounds measures your weight or your mass when you're on Earth, but it would actually change in other gravity situations. So it's not technically a measure of mass. In the metric system, we have the gram. For volume, there's lots of different volumes in the English system. But in the metric system, we will generally stick with the liter. You can also spell that L-I-T-R-E. That's also correct. Seconds, time is time. And then in our English system, we have degrees Fahrenheit. In the metric system, we have degrees Celsius or kelvins. Notice here, Fahrenheit and Celsius are names of the scale. And so it's degrees on the scale, which is why you have that little circle. Kelvin is a unit, just like gram. So we say, when we measure a temperature in Kelvin, we don't say degrees Kelvin, we say kelvins. So you've got 273 kelvins at the particular temperature. And we'll get into that more when we do the conversions too. All right, so how would we measure these types of quantities? Well, for a length or distance, we might use a ruler. Of course, there's various items we could use to measure these things. For mass, we might use a balance. For volume, there's a few different ones, but perhaps a graduated cylinder. Lab. To measure time, we might use a clock, stopwatch or something. And then to measure temperature, we would use a thermometer. So as you've probably learned before, the metric system works by adding prefixes that change the powers of 10 that's used there. So instead of having, like, for example, for length, instead of having a different unit for small lengths versus bigger lengths versus really big lengths, you stick with the meter, but you change the prefix so that you can have millimeter, centimeter, meter, kilometer, megameter, whatever. There's lots of prefixes there. So on the next page, there is a list of these, of several of these. The ones that you really need to know are listed on Blackboard. I think there's only you only need to know kilo, centi, and milli, like by memory, like you absolutely know those. Other ones you can look up. So you'll encounter the other prefixes on your homework, but the expectation is that you're looking things up while you're doing your homework or you're using the book or whatever, so that's fine. On quizzes and tests, you'll just need to know those couple. If you're not real comfortable with scientific notation, like this idea of something times powers of 10, it's a good time to review that. There's some review material in the online textbook, and there's lots of, if you just type in learn scientific notation, there's lots of different guides for that. If you want my help for that, I'd be happy to meet with you sometime if you want some extra help with scientific notation. But it's really helpful with the metric system because everything is set in these nice powers of 10. And then additionally, when we're dealing with very small things like atoms or molecules, or very big things like quantities of atoms and molecules, which we'll get to a little later in the semester, we'll use that scientific notation. All right, so just to give a sense of how much time, sorry, not how much time, what types of units we're going to use for different situations, let's just try this out. So, if you're going to measure the length of a textbook, you might use inches or you might use centimeters. You could potentially use millimeters or meters or kilometers and have like tiny fractions of a kilometer, but it's probably not practical. So we want to pick the unit that best fits the thing we're trying to measure. The distance between the discussion room and the lab, they're right next to each other. So maybe that's feet or meters. maybe also centimeters. Maybe we're saying that there's just one little tiny dividing line between the discussion room and the lab, and we're measuring in millimeters. I don't know. There's no real wrong answers here. How much time do you spend looking for your safety goggles? I mean, hopefully like seconds, but maybe minutes. Those are not the same. I mean, those are not different systems, right? I'm just saying seconds or minutes, like seconds smaller times, minutes larger times. And then how long are you spent working before you graduate? Well, you're probably going to measure that in what, years? Something like that, maybe. All right. So, you can work on those. I think those are all sort of common sense, and they don't necessarily have a right answer either. I just want you to get a sense of what types of units you're using in different situations. Again, we'll get later in the semester in a few units, we'll get more deeply into units where we'll talk about how to convert between centimeters and inches and Fahrenheit and Celsius, that kind of stuff. We're just not doing that right now. All right. So probably the biggest new stuff today is going to be this next part, how to properly make a measurement. So you've all practiced making measurements before, but there's a right way to do it, especially in the lab, when we want to quantify not only the quantity itself, but how precise of a measurement we're doing. Or sorry, we're making. All right. So we can have, first of all, two different types of data. We can have quantitative data, which is described by a number, and we can have qualitative data, which is more descriptive. So quantitative data might be 12 ounces of a latte, and qualitative data might be a robust aroma or a vanilla smell or something like that. One type of data is not any more valid than the other. So often we make the mistake of assuming that because something can be described with a number, that makes that data more valid. But that's not true. Qualitative data is just as valid. It's a different type of observation. So for those of you who were in lab last week, the quantitative data of our measurements were actually not so good because they were just like spoonfuls, like 1 or 2 spoonfuls. But the qualitative data were really helpful when we thought about, how big something got or how warm something got or what color changed, things like that. Another definition that you've probably heard before, but we're going to be more careful about here, is precision and accuracy. So we often use these words interchangeably in everyday life. Something's accurate, something's precise, means the same thing. But in science, it's actually not quite the same thing. Accuracy is how close are you to the actual value. Precision is how much do several measurements agree with each other. So for example, this is often described with targets. So we want to be both accurate and precise. We want to get to the accepted value or hit the bullseye, and we want to be able to do it every single time the same way. We don't want to be way off with no accuracy or precision. Things are just all over the place. Although I might argue in this particular example, if you can see this, let me zoom in here, looking at a phone or something. We may actually say that this has some accuracy because the average of these 3 data points is actually pretty close to the middle, right? So if you make a bunch of measurements and they're all over the place, but the average is actually correct, that's something called random error, and that's actually okay. If we really had no accuracy or no precision, we'd be all over the place and we wouldn't be averaging to the correct value either. But something else that happens commonly in science is to be precise but not accurate. So you take the measurement and you do it the same way every time and you get the same number every time, but the number you get is not correct. And that's something called systematic error. So maybe perhaps your balance that you're weighing something on isn't calibrated properly and everything you weigh is off by a gram. You're going to get really precise data, but it's all going to be off by a gram. Or you are measuring in a graduated cylinder, but you're not looking at the correct level, which we'll get to in a little bit. You're standing up and looking down at it. You're going to be reasonably precise, but you're going to have the wrong measurement every time. So we want to be both precise and accurate, which means that we try to correct for the systematic errors, and we try to be as precise as possible by measuring things carefully and correctly. All right. So when we take quantitative data in lab, we want to communicate both the number itself and how certain we are about that number. So we want people to know something about our expected precision when we communicate a number. So when we write down a number in our lab notebook or in any kind of experimental situation, we're going to write down all of the measured digits, and we're going to write down one estimated digits. These are called significant digits or significant figures, and they contain all of the precise measured digits plus one estimated digit. And this is kind of a new thing, so I'll kind of show you how this works. So if you see a measurement, you know, you're looking at a number in some situation, and it says 40.36 centimeters. What that really means as a measurement is that this number is somewhere between 40.35 and 40.37. Now, different instruments can give a different range, but the important part is that the first three digits that were reported, 4, 0, and 3, are certain digits. We know those are correct. 4, 0, and 3. 4, 0, and 3. And the last digit is an estimate, and we're somewhere around that last digit. Maybe it's not exactly plus or minus 1. It depends on the instrument. But when we write down a digit, that final digit can kind of go either way, plus or minus. That's what we call our significant digits in our measurement. All of them are significant. So the first three are certain. They're absolute. We know that for sure. The last one is estimated, but they are all significant. They're all considered significant. So we write them all down. All right, so let's start with the easiest way to do this, and then we'll work where it gets a little bit trickier. So the easiest way is when you're using a digital tool, because a digital tool has that uncertainty already built in for you. So when you weigh something on a balance and it says 34.70, that means that the 3, 4, and 7 are exact or known or certain, and the 0 is estimated by the instrument. So what this is telling us is that this balance is telling us that we're somewhere between 34.69 and 34.71 or so. And the balance would say on it exactly how much the plus or minus is, but it's something like that. So the last digit could go either way, but we know that it's 34.7 is kind of like in the middle. All right, so what does that mean for you when you're taking this measurement down? This means that in your lab notebook, you have to write down every one of these numbers. So if you see 34.70, don't write down 34.7 because that's a different amount of precision. If we wrote down 34.7, well, then what we're saying is that we're somewhere between 34.6 and 34.8. And that's not right. That's 10 times more of a range than what the balance is reporting. So it's really important that when you write down a measurement from a digital tool, you write down all of the digits that are given, right? Because that communicates correctly the type of the measurement. So if we move then to an analytical balance, which is a more precise measurement, we now get more digits to write down. But we still need to write down all of the digits. Right? So now the 3, 4, 6, 9 are our certain digits, and it's this 9 at the end that's going plus or minus 9, or plus or minus 1. And then this one, even fancier, gives us another place there to measure. And so you can look up some of these terms and such. Again, don't worry too much if you get stuff absolutely right on this. There's not an answer key or anything. It's just a way of taking you through the material so that you're kind of engaging with it and trying it out a little bit. And if you're not sure about any of them, please let me know, either on Discord or on YouTube now or later, whatever. All right. So digital tools are nice. You just write down the number, right? You don't even have to really think about all the uncertainty stuff that we just talked about. You got a number, you write it down, and you make sure you got all the numbers down. Good. Easy. All right. So what happens when you have to make that measurement yourself? This is where it gets tricky. Not tricky, but you have to do it right. All right. So here's some rulers. Just look at these first two here. Actually, first, let's just look at the first one. So here we got a ruler. All right. How are we going to make this measurement? Okay. So when we look at a tool and we want to figure out how we're going to make a measurement, we have to keep this idea of certain and uncertain digits in mind. Now, the certain digits are always expressed by markings on the tool. So you can see here that there are markings at each whole number, 0, 1, 2, 3, 4, and 5. Those are what we call our certain digits. And the reason they're certain is because we can say, all right, this measurement of this thing is definitely more than 4 and definitely less than 5. So it's definitely in between 4 and 5. And even in our current ridiculous world, probably no one would disagree with you. You could probably find someone on the internet to disagree with you. But, it's pretty certain that we are between 4 and 5 here. There's really no arguing that. So we're going to write this measurement as 4. And that's our certain digit because there's a line here. There's a line here. So that tells us we are definitely between those two lines. We are between 4 and 5. So this is 4 point something. The 4 is certain. But we're not done. We don't call that 4. We have to estimate one more digit. The next digit is an estimate because there are no lines here. So one of you might say, well, that looks like 4.5 to me. And somebody might say, well, I think it's over to the left a little bit. It might be 4.4. Probably nobody's going to say that looks like 4.1 or 4.9, but there would definitely be some disagreement. So however you write that down, it's fine. You're making that estimate in between the lines. So we would write this down as 5 centimeters. If you said 4.4, fine. 4.6, depending on how you see it, that's fine. I think that's what that says here too. Yeah. So the 4 is certain. The 5 is estimated. Both numbers are significant. So this is a measurement with two significant figures, two significant digits, the 4 and the 5. All right. Now, what if we change that ruler a little bit and look at this next one? Now we have more lines. So because we have more lines, we have more certain digits. Not only is this measurement between 4 and 5, but we can also see that it's between, so this would be 0.1, 0.2, 3, 0.4, 0.5, and 0.6. So we can also say that measurement is between 4.5 and 4.6 because we can see that the edge of this thing is, right here somewhere. Okay. So 4.5, and those digits are both certain. And now we can add our estimated digit based on where we think this thing ends. So let's call it 4.58. All right. And so, this person said 4.55, whatever. That's fine. It's an estimated digit. We estimated it one way. They estimated it a different way. That's totally okay. Probably because I zoomed in and it, made it look a little different. All right. So notice that these measurements are different. 4.5 means between 4.4 and 4.6. So a bigger range. So when we say 4.5, we're saying, the measurement is like somewhere in this range, basically. When we say 4.58, we're saying it's somewhere between 4.57 and 4.59. So a much smaller range. And depending on the tool, that plus or minus could be even more. All right, so then let's look at this one. Here's probably the biggest source of error in these measurements is when the measurement ends up right on a line. Because it's really tempting here to go, oh, it's 3. Done, 3 centimeters. That's wrong. Why is that wrong? Because there's no estimated digit here. Even when it's on the line, we have to estimate that digit. So a good rule is when you're thinking about these and when you're doing these measurements, always add one more digit than what the lines tell you, right? So these lines tell us 1, 2, 3, 4, 5. So that means when we make the measurement, we want to add the 10th digit, the one digit after the decimal. And so that in this case would be 0 since we are estimating it to be right on the line. So we would call this 3.0 centimeters, not just 3. Remember, if we write 3, we're saying between 2 and 4. One significant figure means it's just estimated. So that's a big, big range. If we say 3.0, we're saying between 2.9 and 3.1, which is actually the correct range that we want to report here. All right, so for those of you following along live, why don't you give this a try? Measure this blue thing using both rulers. Give 2 different measurements. And if you could, just type it in the chat. Be a good way of practicing communicating via the chat. If you can't, just write it down for now. But yeah, let me know what you get, and then we can talk about it. Don't worry, I'm not going to judge you if you get it wrong or something. I just want to see what kinds of measurements you're making. All right, 9.0 and 9.25. Okay. Any other measurements in there? You can agree, disagree. Okay, changing to 9.2. Anybody else out there in internet land? All right, well, I don't know if anybody's out there, but if you do want to put in your measurements, go ahead. Thanks, Garrick. I would agree with you. So here we've got 9 point something, right? Because it's between 9 and 10. 9.2, I think, is a good one. 9.0 is, again, it's a reasonable estimate, depending on how you're looking at this. But I think we can see that it is a bit over 9, so probably 9.2, which you corrected to, is a better measurement there. And then in the next ruler, we can add another place because we've got 9.2, 9.3. The measurement is between those two. And so we can just say, pick something in the middle. If we zoomed way in, we might get a better measurement, but this is meant to be done on paper anyway. So I think 9.25 looks good. So I would call that 9.0 and I would say 9.2 is better and 9.25. Okay, good. All right, so let's move on to a graduated cylinder. And we will use these a lot in lab. We'll use some different types of graduated cylinders, and different tools are going to have different numbers of digits that we take down based on their markings. So the good news is once you use it once and you kind of figure it out, it's always going to be the same. You're always going to estimate to the same place, like the tenths or the hundredths or whatever. But the first time you pull out a tool, you got to figure out how you're going to do that. So let's look at some graduated cylinders and kind of take a look at them here. So this is what a graduated cylinder looks like. They are measured from the bottom up. Start with this one. This one's obviously cut off because we're up into the 30s and we don't see the very bottom. Another thing that happens with graduated cylinders, particularly with water, is that the water has an interaction with the glass of the cylinder, and so it kind of creeps up the sides a little bit. So rather than seeing a straight line, you'll see a curve. And this is true with any kind of thin tube. It's really important that we make our measurement from the very center. Like the center, not the edge. And the reason for that is that's how the graduated cylinder is designed and calibrated. And also that different liquids have different amounts of creep up the sides. So if you look at a thermometer, for instance, like an old mercury thermometer, mercury actually gets repelled a bit by the sides. So the bubble goes the other way, or the curve goes the other way. And we still measure from the middle, even though that's now the top. Other types of compounds might be flatter. It just depends on what's being measured. So if we always go from the center, called the meniscus, that's our best bet. All right, so in this case, how do we measure this? Well, we first have to figure out what that scale is. So in this case, we've got lines at every milliliter, in this case, because it said milliliter below. So this would be 30 milliliters. Then we've got 31, 32, 33, 34, 35, 36, 37, 38, 39, 40. All right. So because those lines are giving us the ones digit, those are our certain digits. So we know for sure that this measurement is, or we know 2 digits for sure. We can call it 39 or we can call it 38 point something, but we know it's 2 digits for sure. And I'm going to say that this is directly on that line, directly on the 39 line. So remember what we just said. If it's directly on the line, we can't just leave it there because that doesn't tell us how precise that is. Excuse me. So we need to say, all right, the 39 is given by the line. And then we're always going to add 1 digit past that. In this case, that's going to be the 0 since we're saying it's right on the line. Okay. Here's a couple more for you all to try. Let's see if I move it up a little bit. Can you see it over my head? So give it a try. You can try to put your measurements in the chat if you want, or just keep it to yourself, or if you're watching it later, maybe pause the video for a second and actually try it. But I want you to actually try to make the measurements. So go ahead and do that before we talk about it. All right, did you have a chance to try some of those? Hopefully. Oh, great, Garrick, thanks. So 6.6, 20.0, 2.55. Okay. Anybody else? I think you might be the only one typing today. That's okay. All right, let's look at this first one. So we've got a measurement here, a little bit different from here because we've got 6 to 7. And the lines in between then must be the tenths. So 6.1, 6.2, 6.3, 6.4, 6.5, 6. Okay, so the level we're going to say is right on 6.6. remember, that's a line. So those are both certain digits. So what does that mean? That means we have to add one more digit. So this should be 6.60 milliliters. Because the 6.6 has its own line. And so the zero, the hundredths, that's what we would have to estimate. And if we're saying it's right on the line, we're estimating as 0 right there. All right, so then for this one is more similar to the first one I think that we tried. So the lines here, we've got a big line for 20, a big line for 30, and it looks like we've got the ones in between. So 21, 22, 23, 24, 25, 26, and so on. And the liquid level is clearly right on the 20 here. So we would again say that's 20 and then add one estimated digit. So that would be 20.0. All right, and then the last one, this one seems like maybe not on exactly on a line, maybe like about there. So where is that? We've got lines for 2, we got lines for 3, and a bunch in between. So those must be 2.1, 2.2, 2.3, 2.4, 2.5, 2.6, 2.7, 2.8, 2.9. So this liquid level is in between, since we're going from the center, right? The liquid level is in between the 2.4 and the 2.5. Let's say it's about halfway or so. So we would call that 2.4. Oh, happened to my, there it goes. Okay. 2.45 milliliters. All right. Okay. So that's how you make a correct measurement. As I said, the major sources of error here, one is when it's right on the line. It can be hard to remember to put that extra 0 past the line. Another one that sometimes comes up is we're used to thinking in fractions sometimes. So if it's right in the middle, we say 2.5. And if it looks like it's kind of on like a quarter of the way there, we say 0.25. Because we're thinking, oh, it's like a quarter, 0.25. But we can't do that, because if you say 0.25, you've added an extra digit. You're actually estimating 2 digits instead of just 1. So if you want to estimate 1 digit, just estimate 1 digit. Call it 0.2 or 0.3 or something like that. All right. So that measurement, those are all called significant figures. And it's important to take a measurement with the correct number of significant figures because it communicates the precision of that measurement. You can't just put an arbitrary amount of zeros based on how sure you are of the line on your instrument. There's a specific procedure to getting the correct number of digits. Writing 3 is different from writing 3.0, is different from writing 3.00, is different from 3.000, and so on. A calculator treats all those numbers the same way, but when we're talking about a measurement, those are different. They communicate different levels of precision. So we want to communicate all of the correct levels of precision, and we can do that by counting the number of significant figures. So in these balance readings here on the left, they all have different numbers of significant figures. In the graduated cylinder readings, a reading of 43 has 2 significant figures, a reading of 43.0 has 3. Now, the way if you're just looking at a number, you didn't actually take the measurement yourself. The way you can figure out the number of significant digits is just by some rules here. So first, non-zero digits are always significant. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Whatever those are always significant. Zeros are sometimes significant and sometimes not. And this is where it gets a little bit tricky. But if you think about the way you make a measurement, hopefully that helps. So there's some basic rules here. But basically, zeros after a number after the decimal place, like here, are significant. But zeros in front of a number, like these, are not significant. So this they use different colors or something, but this number 0.00340 has 3 significant digits: the 3, the 4, and the 0. And the reason for that is that 0 is before a number. 0 is before a number, and 3 is after a number. 3 is after a number, and 4 is after a number. 3 is before a number, and 4 is after a number. 3 is before a number, and 4 is after a number. 3 is before a number, and 4 is after a number. 3 is before a number, and 4 is after a number. 3 is before a number, and 4 is after a number. 3 is before a number, and 4 is after a number. 3 is before a number, and 4 is after a number. 3 is before a number, and 4 is after a number. 3 is before a number, and 4 is after a number. 3 is before a number, and 4 is after a number. 3 is before a number, and 4 is after a number. 3 is before a number, and 4 is after a number. 3 is before a number, and 4 is after a number. 3 is before a number, and 4 is after a number. 3 is before a number, and 4 is after a number indicate the magnitude of the measurement domain. Like, are you measuring something big or are you measuring something really small? But they don't really tell you anything about the precision of the measurement. And it's actually the same thing with numbers with zeros at the end that don't have decimals. So if we said 100 as a measurement, we don't really know if that's 3 significant figures or just one. If we say 1,000,000 or 1,500,000, we don't really know how many of those zeros are significant or not. So are you measuring, like, are you using a ruler that has actually goes down to the ones place? Or are you just using a giant measurement that has blocks on it? So because of that confusion, if we really want to carefully communicate significant figures, it's a good idea to use scientific notation, because then the measurement is separate from the magnitude. So if we say 6.02 times 10 to the third, the 6, the 0, and the 2 are significant. The 10 to the third part just tells us how big it is. So this is actually 6,020, right? So that would have 3 significant figures. But if we write this number as 6,020, it's not clear how many significant figures that digit has. Does it have 4? Or does it have 3? Right? So it's confusing. So if you have a number like this and it's important to communicate precision because it's a measurement or something, you should use scientific notation to do so. So this measurement, the next one underneath it, 6.020 times 10 to the third, is also 6,020. But this time, all 4 digits are significant. And that's very clear when we see it in scientific notation because we see the extra digit. But if we just wrote 6,020, we wouldn't really know how many of those are significant or not. So, this gets a little bit subtle and can be a little bit tricky. And if you've taken physics or chemistry in the past, you might have learned to do calculations where you maintain your significant figures. So one of the things that we do is when we get a measurement like this and we want to do a calculation with it, we have to use some special rules to make sure we're carrying our precision throughout the calculation. In this class, we're not going to do that. That's not one of the objectives of the course. So you don't have to learn to do that. If you want to, I'll show you how, but generally we're just going to round reasonably when we calculate things and go, okay, well, 2 decimal places, 3 decimal places, about the same. But there are real rules for carrying that precision through. So please review scientific notation if that's not something you've thought about in a while. Practice taking measurements with significant figures. There's some stuff up on Blackboard. There's a homework set up that you can look at. And then there will be a quiz. I think it's going to come up on sometime this weekend, and it'll be due next week. So you can test yourself a little bit on this as we get into the next chapter material next week. So as usual, send me any questions you have. If you didn't get a chance to join us this morning, hopefully you're watching at home. I will post a more permanent schedule for live streams today. I'm getting back the results of the survey, and it looks right now like it's going to be Monday evenings and Wednesday mornings, but we'll see if that changes. So thanks, everybody. Have a good weekend. Hopefully it wasn't too much for you this week. I'm excited to meet the other half of you next Wednesday. Bye, everybody.